Continuation of section 4.1 on extreme values of functions. All right, if you recall, we've looked at local minimum. Here they occur at these 3 points. That's a local minimum, and a local minimum. And we've seen too that that's an absolute minimum occurring at the whole, when we're talking about the closed interval from A to B. And then, of course, we've got that local maximum here and right here. And then that's, of course, the maximum value among the local maximum. It becomes your absolute maximum. Now, if you look at these two interior points, the slope tangent to the line at x equal to E and at x equal to C, the slope of the line tangent to the curve is 0 because you've got a horizontal line. Okay, so let's look now what this means and how it will help us find local extreme values. By Theorem 2, the first derivative theorem for local extreme values. If f has a local maximum or minimum at an interior point C in its domain, and if f prime exists, that means we can find its derivative there, then f prime of C is equal to 0, which makes sense because this one, the slope of the line tangent to these two local extreme values is 0. Again, what does this theorem 2 say? Well, it assumes already that f has a local either max or min and has a derivative. So the only places where f might have an extreme value, whether it's local or global, that means absolute min or max, would be an interior point where f prime is 0, an interior point where f prime is undefined, and at the endpoints of f. Let's go back to the previous slide. If you see this interior points C, E, and D, at C and E the derivative exists and it's equal to 0 right there. Now at D, we don't have a derivative because of the way that you've got a cusp occurring here. There's no smoothness where you can attain a 0 slope. So let's look at the definition of what a critical point and why this is helpful for us. An interior point where f is either 0 or undefined is called a critical point. So what does this mean? It's just saying that it could, a critical point is where the function has a 0 slope, or if it's undefined, that means it may not exist there, or it's a vertical slope. But that doesn't guarantee an extreme value, okay? But they are good candidates. Let's check out the next example. Critical points without extreme values. Letter A is a cubic function, y is equal to x cubed. And if you look at this, y prime would be, of course, 3x squared. Set it equal to 0. That'll just give us x equal to 0, which tells us that the slope of the line tangent to the curve at 0, which is running through the origin, is 0. So you've got a horizontal line tangent to the curve. However, that's not an extreme value right there. We don't see any valley or hilltop. Okay, what about letter B? Letter B, you have a cube root function, y is equal to x to the 1/3. Take the derivative. Y prime would be, bring down 1/3, then x to the negative 2/3. If you set that equal to 0, then it will be undefined at x equal to 0. But y equal to x to the 1/3 does not have an extreme value occurring at 0. All we have is just a line tangent to the curve that's vertical. Okay, so but these are critical points that may possibly give us an extreme value. How to find extreme values or absolute extreme values of a continuous function on a finite closed interval. Remember, it has to be a continuous function and we've got to have a closed interval. The first thing we do is evaluate f at all the critical points and the endpoints. Take the largest and the smallest of these values. That's it. Now remember, to get the critical point, you take the first derivative and then set it equal to 0, whichever makes it undefined or 0 becomes a critical point. Example, find the absolute maximum or minimum values of f of x equal to, this is a quadratic function that's translated to the right by 2, and then it's vertically translated below down by 3 units. But we are confined on the interval from 0 to 5. Okay, the first thing we need to do is get the derivative, set it equal to 0 to find the critical points. There we have f prime is use the power rule on the whole quantity x minus 2. And then the derivative chain rule, what's the derivative of x minus 2? That's 1. And of course, the derivative of 3 is 0. So all we have is just 2 times x minus 1. Set it equal to 0. Divide everything by 2. Then you get x equal to 2, and that's your critical point. So we've got one critical point. And then what's the next step? You evaluate at the endpoints and at the critical point. So we'll compare the values of f at x equal to 0, 2, and 5. All right, f of 0 is equal to, that's 4 minus 3, that's 1. Okay, f of 2, we see that this will make it 0. And in fact, that's actually where the vertex is. And the f of 2 would be negative 3. And then, of course, the last one we have to evaluate would be f at 5. And f of 5 is plug in x equal to 5 into the x. Then that's 5 minus 2. That's 9 minus 3 equal to 6. So just compare all these three values, and that gives us the absolute minimum and the absolute maximum occurring at x equal to 5, and the maximum value is 6. And here you see that when x is equal to 2, we have an absolute minimum occurring right there, and then an absolute maximum occurring at x equal to 5 with a value of f of 5 equal to 6. Another example, find the absolute maximum and minimum values of g of t equal to 8t minus t to the fourth on the interval from negative 2 to 1. Again, take the first derivative, set it equal to 0, and then of course we find the critical points. G prime of t is 8 minus 4t cubed, set that equal to 0, which means we put negative 4t cubed on the right side, divide both sides by 4, and we see that t cubed is equal to 2, which means the cube root of t, but the cube root of t is not in the interval from negative 2 to 1. Okay, so that means there is no critical point in this interval. So all we just have to do is just compare the endpoints. All right, so when t is equal to negative 2, what is g of negative 2? Just plugging in the original function, and we see that g of negative 2 is negative 32. And when t is equal to 1, that's the other endpoint, g of 1 is 7. So this becomes your absolute minimum, and that's your absolute maximum. And here is the graph of the function. That's where the absolute minimum occurs, and that's where the absolute maximum occurs. And you see that the square root of, or rather, sorry, the cube root of 2 occurs right here, and it's outside the interval that we have chosen, so it has no bearing on what is the absolute extreme values of the function on this given interval.